Hi everyone, my name is Arun Surya. So I'm a scientist at IIA, and I usually work, mostly my interests are in developing instruments for telescope. Uh, Ravi actually did a great job of already setting up the stage, explaining different concepts, and as with the theme of this workshop, right? It's about theoretical but also demonstration and the latest in the field. So the three facets are discussed, which will be enriching for you. So let me just start. Ravi already explained a lot about telescopes, and how many of you have actually seen through a telescope? Can you raise hands? Almost everyone, or okay, so considerable number of people, and there are also like our outreach team here also does sky watching sessions, which you can use like a smallish, I say popular size telescopes to see planets. Now it's a good time because there are like three or more planets like really visible in the night sky, so it's a good time to watch it. And if you go watch through a amateur telescope, I don't want to use it also like the language of amateur. It's more popular and available telescope. You see, then you go to an observatory where scientists works, and the telescope little bit looks like this. Usually, when you start talking about telescope, the main thing is people always ask about eyepiece, right? In amateur telescope, you always use an eyepiece to look through things. And in the general difference in scientific astronomy, or like the professional astronomy double code, is that a lot of the science comes not just watching through eyes, and there is usually no provisions to watch through eyes. It's mostly through instrument attached to a telescope. So when you usually go to an observatory, you see a telescope and you will see a lot of things attached in the bottom. And Ravi had already explained about different types of telescopes, right? And you have heard about Cassegrain, Coude, Prime Focus, etc. Right? What do you think this telescope is? What kind of telescope this could be? The clue is instrument is here, right? It's at the bottom. Light comes from the top. So one little picture is like light comes from top, hits the mirror here, goes, there is a secondary here, comes back, and there is a hole. The primary mirror has a hole through which the light comes back, and there is an instrument. So all telescopes usually work in this fashion. You have a telescope, and then you have an instrument. Now let's go and see why you need instruments. Why the need for instruments? How are they usually aligned? So a general perception, I think you already know this from the previous talk. If you have two stars separated at angles, a telescope you can also imagine as an instrument that converts angles into distances. So if you look very far away, you see things in angles, right? Like you look at moon, it's very far away, and you don't say like moon size. You say, okay, moon is 30 arc. How much is moon size? Anybody? You know how much size of the moon approximately? Angular size in the sky? Half a degree. Yeah. So you talk in terms of angles. And what does a telescope do? Convert angles into distance in the focal plane. So that is what mostly is done. So if you have a telescope, two stars, they are separated here. And this is what the plate scale also that Ravi talked about. The distance between these two stars depends on the focal length of the telescope. The plate scale, the distance that an angle covers is decided by the focal length of telescope. And this is a very interesting picture. It's actually taken in a telescope in Chile. And what they did was like put a large screen on one of the focal plane. And what do you observe here? This half a degree kind of moon, right? Look at the size of it. This person is there, so you can kind of like refer it. The size of the moon is this much. So this is one of the issues when you go to larger telescopes, because you essentially, especially in Cassegrain mode and other modes, the focal length is so large that the size of the image becomes so huge. And now, how do we put any instrument there? So one of the things that what we call instruments, or these thing I showed you, right? Main purpose of that is to act like this. It essentially is like a focal reducer, what you call it. Essentially what it does is convert this large focal plane, which is around here, to a small, especially with the detectors we use, right? If you have to put like a DSLR camera, a full frame camera, these are like 20 mm in size. Now, my target is that the very large field of view that is imaged in a very large scale by the telescope, I want to reformat it into my detector size. So usually a lot of the imaging instruments in telescope essentially does this. It actually images this onto a detector, and it has two components. One is the focal collimator. So a collimator is a lens that has decent enough size to cover the different fields of view, and then you have another lens which is the camera lens. So the collimator will make the focus beam comes diverging, hits it, it makes everything parallel again, and then the parallel beams from different field of view hits the camera lens, and then it focuses again. Now the plate scale here, the size of the images here will depend on three parameters. One is f telescope, f collimator, the lens, this lens, and f camera. So these three combinations decide what the size of an image on a detector is. So this is generally the format of a general instrument in a telescope. So before we go, I wanted to do a small demonstration also. Like usually people don't see what a telescope is. So I had this parabolic mirror. So this is a parabolic mirror. So usually for Newtonian type telescopes, simple amateur telescopes, we have this mirror, and this mirror is kept, it's inside a tube. That's why sometimes you can't see it, and usually, and the other thing is when you hold optics, these are also important lab things. Like you always hold it in the side. Huh? This I'm little more careless because we use it in a lot of things. But usually also you put a gloves on and like you do little care handling optics, and you put it here. So this acts like a, this is our primary mirror, right? So a lot of the imaging, what happens is that light goes, hits it, and focuses somewhere in between. And this thing, I will tell you already that what is the focal length of it. Its focal length is around 90 mm. Hmm? So now, sorry, 90 centimeters, sorry, not 90 mm. So 90 so it's almost like a meter size, focal length of it. Now, how do we like picturize it? This is like a gimmicky laser thing to tell people how the parallel rays work. So, like this is the other caveat I'm telling. All experiments usually fail initially. It's very difficult to get things done. So let's try it if it works. So let's switch it off and let's see. Okay. Okay, let's little more luck we need. Yeah, that's much better. Do you see like the focus is coming? It's little bit angle is tilted. That's why. Let me little bit raise it. Adjust it. Yeah. Now you see a parallel beam. It's not parallel, right? It's diverging. Yeah. Now it's more parallel. But do you see the two rays like focusing on? It's I think the one of the things little fainter. Yeah, I think battery of this is gone. But do you see like a parallel beam going and it kind of like converges onto a focal point? And if you had multiple beams where it will intersect is where uh, you will actually see it. And I will do the battery again. The batteries are running out very fast on this, but that's one of the ways you can visualize rays using lasers and getting it pointed, because the lasers are very straight. It actually acts like regular, like a light ray. So you can visualize a lot of these things, ray optics using lasers, but also with these green lasers which are powerful. You can see it because it's powerful. You have to be little careful it doesn't hit your eye. So we'll come back to this demonstration. And the next thing, yeah. But did you guys see like the two beams coming and it converging around here? So that's approximately where did it converge? Like around this region, right? And this is the focal length of this primary mirror. So what usually for like a Cassegrain Newtonian telescope, what it happens is that even before the focus, you put a mirror here so that the light is reflected this side. And this here you put an eyepiece, and that's how a normal telescope, most of the amateur telescopes work. Now, going to, so where were we? We were telling about imagers, and we told that imagers are generally a collection of like optical elements that convert the large sizes in the focal plane of telescopes into fit into the detectors, which are usually of smaller size. Yes, go for it. No, 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 go for it. You can interrupt me anytime. Yeah. Yes. Yes. It will have. So what happens is that you can't float a mirror, right? So what happens is that people usually put like a thin thing and you stick a mirror on top of it. Now the problem is you are blocking light first of all. Some light will not enter because you are blocked. So other thing is that telescopes have this thing called diffraction. So the spot diagram that you get from a circular aperture is usually something called an airy pattern. It's like a like a sin square function. Yes. Now, when you put a mirror and like a stick and a mirror on top of it, what happens is that diffraction in physics, you know diffraction, right? So how you compute the pattern on the detector is that you take a Fourier transform of the aperture, how it will be seen. Now, if you put an obstruction and if you take a diffraction pattern of that, that will have more sharp things and side things. So it will not be symmetric. It will, depending on how you have put the mirror on the center, it will change. That's why some telescopes you can see side spikes, right? Like if you have four spiders as in four rods that are holding the mirror, sometimes you see spikes. And some other telescopes you will see some other pattern. So these patterns vary from telescope to telescope depending on how you hold your secondary mirror. That's the main thing. So now we are in imager. So Ravi already talked about this thing, right? This is your regular telescope where you have an eyepiece. And our thing is similar to that only. As in the second lens also makes it parallel. What is the difference? The difference here is that the size of this is usually so that my eyes can see it. So the cone of light of this parallel beam, it should be like the size of my pupil. But in the case of telescopes, we are not putting my eye anywhere in the close. My goal is finally to image things into my detector. So that's not the case. So instead of using this, and usually that is the one reason why the eyepieces you look through, right? How much are the, if you have to buy an eyepiece, for example, how do you buy it? You have seen like 10 mm, 30 mm, 20 mm. That is how you buy. And these are very short focal length. That's because the more shorter it is, and I keep it, the beam coming out of it will be also short, and it will be like close to my size of my pupil, so that I don't lose any light. So that's the main difference between like an amateur kind of telescope and a general professional telescope. Now, the more important thing that is significant to this is plate scale. So you already know this formula from the previous lecture, which is that the focal length decides the size of an angle on my focal plane. If I know the focal length of a telescope, I know how much is the distance covered by a certain angle. Now, I have put extra things in between, right? If it was the case of this intermediate plane, you would have been correct. But what happens is that I have put two more things. So how does this change the focal plate scale? Basically, the equation to find out the plate scale when you have two of these components is this. You have f test, earlier it was f theta. Now you have f 3f. One is f tel, then the collimator f is below, and the camera is top. Now, if I have f tel, which is large, right? So the plate scale is large. Now I want to reduce it to a certain extent. What should I do? I have these two to play with, right? I can adjust the focal length of the collimator such that it is thoda larger, and f cam, which is the focal length of the camera, I'll adjust such that this ratio f collimator by f camera is like larger. So the inverse. So you get a less focal length telescope in a way. So this is used to adjust the angles to your instrument. Now, I explained you a little bit of how things are with instrument imager. Now let's look at a real imager. So Ravi had showed this Keck telescope, right? It's like a beautiful two 10-meter class telescopes sitting in Hawaii. It's a mountain in Hawaii, and this is one of the most used imagers in that telescope. Now this is a schematic for it. It's not the actual optical diagram, but it tells you a lot of things. One is that the collimator, so the light from telescope comes through here. So till here is the light from telescope. So this is the instrument, that cube. Now you have collimator. So collimator need not be one lens. You can use a combination of lens to get also the same effect. So these three lenses acts like a collimator, and these three lenses acts like a camera. So after collimator, you have a parallel beam, then this camera focuses it. Now there is also something in between. What is this? So this is the question. So this is also something that imagers use, like the imaging cameras are used that are used in different telescopes. This also is there. So let's see. So electromagnetic spectrum I won't go because it has been already explained. The important thing with astronomy is that wavelengths become very important. To deduce a lot of science out of observations, you need an extra parameter, and that's not just the spatial thing, but also the other dimension of wavelength gives you the real science. So there are different wavelengths to probe different science cases. It's explained a lot here, but visible and infrared are mostly the ones that are, and radio are the mostly the ones that we observe from ground. And for a lot of the other wavelengths, we go to space to observe them, because atmosphere has this thing called atmospheric window. It doesn't allow every wavelength to come and to us. So we usually operate in this here. So this gray thing, it's your opacity. So you can see invisible light is, you can see most of it. There is a window. So there is like a window, means like it's coming. But then when you go to infrared, there are partially some wavelengths there is full like transparency and some is opaque. So you have to make your instrument in such a way that you look at things in little bands of wavelength. And that is what a main part of imaging is, when you go to different wavelengths. Now, now I'll come to what was the thing in between. So these things are called astronomical filters. So I am interested in wavelength, and I am interested in isolating wavelength. So if you see like a colored sheet, right? When you look through it, you see green light coming through, right? So what's the reason? So one of the reason is that these are like dye-based absorption filters, where, sorry, one second, where some part of the light is absorbed by it, and the other part is like allowed to pass through. So that gives you like a band pass where light is coming and some parts is blocked. So that's one way people make filters. The most used ones are called interference filters, which are actually like a layers of dichroic layers actually coated on. So they're like maybe like 100 200 layers. They are pasted on each on top of it, such that some wavelengths are reflected off and some wavelengths are passed on. So you can tune this coating in such a way that only a certain band of light is passed through. So this usually are used in astronomy, and this is one like at a certain time these were like very popular, and it's also has a lot of scientific significance. These UBV filters, which are actually span a certain band of wavelength. So when you look through a U filter, you look only the wavelengths from here to here. B filter from here to here. B this side. Now, why do you use it? Just by using filters, you gain. So this, whatever the filters I told you, right? Interference, absorption filters, these are the filters that are used here. So an imager is usually like a collimator, a filter, a camera, lens assembly, and a detector. This is usually like a usual imager works in most telescopes. Now, what does filter photometry? So essentially, you are again measuring light. So even when you're measuring light in filters, you still can deduce a lot. What you can deduce is that you observe a star in a certain different bands. You can say, huh, this star is bright in this filter, but not in this filter. So the difference in this, the light you get in different filters can give you an indication sometimes the temperature of the star, because the star has a certain profile with a certain temperature. And if you have a, you know, have people study black body radiation. So a lot of stellar like flux profiles kind of reflect like a black body radiation, right? If you think about it, and then if you measure UVB, if I take a light here, here, and I measure the differences, I can kind of predict which of these stars are there, what I'm measuring. So this essentially give you an indication of like the temperature of the star. So this was used earlier when spectroscopy was not a big thing. It can also tell you, this is this famous HR diagram. So when you measure filter light in different filters for a large number of stars and plot it against the luminosity, you can deduce a lot of interesting things about the stellar population. So this is also, I think the coming lectures you will hear more about a lot of this science. But this using filters and images is one of the ways you actually learn a lot about stars. Now, there are other things you do, I think Ravi showed you like an image of star, right? And H alpha is like this tiny line uh, in visible wavelength. And if you can make a very narrow filter because you have the technology to coat, make these interference filters, and you make a very narrow band filter, or you use a certain kind of things called Fabry-Perot echelons, etc. You can tune into a narrow region, then you see sun in like a very narrow band. So then everything else is isolated. Parts of sun which are dominant in H alpha, chromosphere, etc. You get all the, you can concentrate and you can isolate features using narrowband filters. And also, if you see galaxies through different filters, like if you see, sorry, if you see in visible, you can see like a galaxy and you can see this obscuration, right? What is this obscuration? Anybody? When you look Milky Way also, it looks little bit similar, right? How many of you have seen Milky Way? Nobody? You have seen? How did it look? Did it look like a darky patches? So these are like gas and dust. And what happens is that in visible, this will block the visible light. But the more you go towards infrared, in different bands, you can see through this dust. So so this is generally use of filters. So now let's come to spectroscopy. So here earlier we were looking at the spectra of the wavelength information we are getting in batches. I will say it's like a coarse spectrograph. You're looking like a bucket. You have a large wavelength span. You are seeing light coming like this bucket. U V V, huh? The three buckets, and you still get enough information. But what I really need is to understand the real uh, things like composition, temperature, motion, etc. To deduce a lot of information for my science, I need something more like spread. Like I don't need just measuring light of a certain bandwidth. And for that, you need to, the light from the whatever object you're looking at, you need to disperse it. So if you look at this spectra of the star, this is the Altair. So it's one of the bright ones. And you take a spectra, which is like if you put a prism, you get like a spectra like this. And you see absorption bands, you see some lines. And so generally when you take a spectra, right, you are an astronomer, you take a spectra, you have got some spectra, you reduce it, the data will look like this. Essentially, you will have an x-axis, y-axis. The x-axis tells you wavelength and y-axis tells you brightness. And this tells you at each wavelength how much is the flux you are receiving, how much is the light you are receiving. And there will be some parts where there will be absorptions. And depending on the absorptions, you can tell something about the star. You can tell something about other things about the system that you are looking at. So for all this, you need a system where you are able to take a spectra. So, so this is what I was mentioning. The generation of spectra itself, I think other people will talk about it, but it contains things like a continuum because your stars essentially will have a black body profile. Plus, it will also have things in the outer layers, right? Or hot gas. Then you will have emission profiles. It gets excited and you will have emission lines. Then when your light of the star goes through colder gases, then you will have absorption lines. So all of this, the continuum, the emission, the absorption, everything combined gives you the stellar spectra. And this gives you information about the target you are looking at. Now, how do we build it? I told you about like what is spectroscopy, but how do you build it? You essentially need, telescope is something that converts angles into distance. We need something similar. We need something that converts wavelengths into angles. We need to disperse. We need each wavelength in different angles so that like the light is spread in each wavelength. So there are two ways. One of the thing is prism. everybody has seen a prism, right? Like prisms are like light goes, it goes in different directions. Each wavelength will come out in a different angle. So you can see different colors in different angles. Now the other thing people use is called a grating. So gratings are usually like this. It's like a very high frequency lines will be etched onto a glass blank or like any substrate, and it will give you something out of a phenomena called diffraction. You will have this thing like you will have a zeroth order. When light enters a diffraction grating, it creates different orders: zeroth order, first order, second order, and in each order there will be dispersion. Light will be dispersed into different wavelengths, and the dispersion itself depends on the order. So the larger the order you go, the more the dispersion will be. Hmm? So So this is a simple student grading, like it's just like a simple grading. And if you look through this in different lights, you can see the spectra. Hmm? I'll pass it around during the talk, and you can look through it. Now, if you look at solar light with it, you'll just see, what do you see? The light. You see like red. Through a prism also you have seen na solar light. It's just like a continuum. But interesting things happen when you look at different things with it. So I will also suggest you to look at the screen through this. And this is a little slit. I'll come to this, but I'll pass it around just after the next slide. So what you should do is put a grating like here, and like point, there's a hole in it, and you have to point it at the LED light on the top and also the screen, and then check what is the difference you see. So, and then we'll discuss it later why some things are looks so funny in the LED, the screen, and why some things look different in the thing. So just to explain that, a simple spectrograph generally is like this. You have a star, the telescope focuses light, and I already told you this collimator business and camera business, right? It's like expand the beam, make it parallel, and focus it. The only difference what usually spectrographs do is that in the parallel beam, we introduce the disperser. So grating is introduced in between the parallel beam. Now this splits the light into different colors. So red will be here, blue will be here. Now when I put a camera, it will focus it in different parts of the detector, and that's how you get a spectra. So the issue is that if I build something like this for a single object, it will also see light from other stars also, right? And what will that do? The problem is this. So if I had a field, I have an imager, and I image like this giant field where you have a lot of stars, etc. Now, in the same imager, I put a grating. Then you get this spectra. So each of this line is a spectra because it's dispersed in wavelength. Now, the problem is, do I get the spectra of everything? There is some fundamental problem here, right? This technique is called slitless spectroscopy because we don't use any slit. But the main issue with this kind of thing, where you just put a grating in a camera, is that the light from like two things very close together, right? The spectra will like overlap, and it's very difficult to de-blend it. So everything will be overlap. It's just like a mess, the whole mess. So there you can't get for a single object, it's very difficult to get the spectra. So what will we do? The one thing we do is that at the focal plane, we always isolate. We put a slit. We just isolated the focal plane one object, and the light from this star will never enter my spectrograph. It's just blocked. So only one object is actually passed through. So I get the spectra of one object, and that's how a normal spectrograph works. So, let me put the grating. Okay. So this this is the Pringles box, and this is sometimes very nice to make this experiment. So this has a tiny slit here. So what I want you to do is like pass around this, and you look through here, like you see the light, but then you look through the grating, you can see the orders. And now you look through the LED light, but then you look through the screen also. So the two things you have to do. So I'm starting from here, so you can just go around while I continue my talk. Okay. So you have to first look at the top one. Do you see the hole? So you have to hold it a little away so that you see the spectra. Do you see the spectra? Huh. What do you see? Like, do you see a continuum thing? Huh? It's a rainbow, right? Now look at the screen. What do you see? Is it that continuous? No, right? What do you see? Do you see anything particular? How many lines do you see? It is bright here, but in that's because the screen is not brighter. But do you see lines? True. So these screens are generally what these screens are LEDs, right? Like in your phone, you have RGB, right? So you have three LEDs. So this whole screen is filled of each pixel. There are like three LEDs. So each emits in like a certain wavelength, and it's a combination of that LEDs gives you the perception of color. So, but when you look through the spectrograph, it clearly sees three particular lines. Now the clarity is less because you have to, this is a what you call Jugadu spectrograph. Now for an actual spectrograph, you will see three lines. This we don't see. So yeah, so we'll continue. You can just pass on and look through this. So this simple slit spectrograph essentially does is that it selects the light, passes and gets the spectra. Now, how this is the HCT, which is the Himalayan Chandra telescope. This is one of our most amazing observatories in Handle, in Ladakh, near Ladakh, and it has an spectrograph called HFAS. It is also a slit spectrograph. So now we are taking a spectra of these two objects, and I want to observe these two objects called spectra. Now they have all these objects next to it. But what I will do is like I'll put a slit, only select these two objects, and then the light passes through and I get like a whole spectra. So this allows you to get a spectra of individual targets. Now the next thing, the same slit spectrograph, right? There I have used slit. The slit can be longer. And even if, because it is one line, the other side by side objects won't interfere. Now if I put it through a galaxy, so this is a nice example of it. If you put it across a galaxy, you get a spectra like this. Now do you see something funny about this spectra? This is the spectra. You see the wavelength, right? And you see the galaxy is bright here in the center, right? You see, and this is in negative space. So the more darker means more brighter. So this bright patch is in the center of the slit. Right? This is the center of the galaxy. Now, at a particular wavelength, this bright thing is at a particular wavelength, but these side things, right? This is little shifted. If you look closely, this is little shifted. It has a weird S shape. Why do you think that is? Anybody? Temperature, yeah, but the temperature changes affects more continuously. This is like a single emission line is getting shifted. So this is one particular line. Hmm? So this is the H alpha line. If you look, 6652 is around where H alpha. You see the hydrogen lines, the one H alpha is there, and this line is little shifted. So that's a good thinking, because temperature does shift, but it shifts everything continuously. So this, uh, that's a good point. Motion. So what is happening in this galaxy? Is this galaxy static? It is moving, right? So the interesting thing is there is something called Doppler shift. So what Doppler shift is, when something is moving away, that is moving, receding from us, the thing is red shifted. The lines you will see will move little bit towards the redder wavelengths. And while something is coming towards us, things will move towards blue side. Now this is very easy to calculate. The formula for this is that the shift in wavelength divided by the wavelength will be equal to the velocity by c, and c is the speed of light. Hmm? So take note of this formula. Very simple things, right? Can you tell me the velocity of this galaxy? How much is the wavelength lambda in this? What is the lambda in this case? This is this line. So this is around 6561 you take, or 6560 also you take. Hmm? Now this shift, how much is the shift? This is 60, this is 50. So it will be around 1, 2, 3, 4 units. So around 40. I can calculate 40. So 6640, 6650. So my difference delta lambda is around 10 angstrom. So 10 angstrom is the delta lambda. Lambda is 6650. Velocity of light, velocity of light, 3 into, yes. So C, now V, somebody has to calculate. You can do it slowly so that by end of my talk, you can tell me. Do I have time? I have a little bit time now. Okay. So this is another thing you can try out. Like if you see this thing. So this is Doppler shift. So essentially, like, you can use spectroscopy to detect things, moving things. If you have a good resolution for your spectrograph, I'll come to that. Now, slits are like the things that are cut out. So I say I isolate a star. What does this mean? What I mean is that I block. So I have a metal plate with like a small thing, like that Pringle box. No, it has something cut out. So it's a physical block. Other thing you can do is put a fiber. So fibers also collect light and take it out somewhere else, right? So what people do is like put a fiber. I know where the star is falling, so I'll put a fiber on top of it, and the light, the same fiber will come somewhere else and put the light away. Like the diverging light will come from the other side, and this plane is called the pseudo slit. And then again everything remains the same. It just goes, disperses, detector. The difference here is that, what do you think is a big difference from fiber and slit spectrograph? What could be? Okay, I'll tell you what it is. One is, so this is a fiber spectrograph in HCT. HCT is our telescope. So this is the telescope there, and you see these things are the instruments attached to the thing. Now this box you see is my Hanle-Escher spectrograph, one unit that is attached to the telescope, which collects light, and the starlight will fall onto a fiber there. Now fibers are interesting because fiber you can bend, take it anywhere. The light will still reach. Have you seen this like a flower pot kind of fiber thing you have seen? No, like the light will always, even if you bend, the light comes on. So what people do is like put the fiber here, But take a long fiber. Sometimes these fibers are like 20, 30 meters, but they will take the light to an entirely different room or floor. You can take the starlight with very like not so significant loss of energy. You can transmit all that light into another room where you build your spectrograph. So that flexibility is there. And sometimes you want to keep your spectrograph stable. This is one of the things used. Otherwise, everything I have to put it on the bottom of my telescope. Now, the other thing people talk about is spectral resolution. So Ravi talked about something called spatial resolution. I have a telescope. I'm looking at very too close things, but I can't resolve it. So even if you take, when you're looking through a telescope, no, like a binocular, and people usually say, can I magnify it so much? Suppose I use 100x magnification. Will I see so much details? I keep on increasing the magnification. Will it still give me all the information? No. The reason is that the limit of resolution is decided by diffraction. If you have an aperture, the information that will be there that you magnify is decided by the size of the aperture. Similar to this ad concept, we have something called spectral resolution, which is basically how close wavelengths can you separate out. And that is decided by something called this line spread function. So essentially, all spectrographs are images. Kind of, you can think of as one slit is getting, or like one fiber is getting imaged here, but at different wavelengths. So this is essentially the image of a fiber in different wavelengths. So now, okay, if this is an image of a fiber image will have a certain size, no? So we can only see delta lambda up to a certain extent, because the fiber size in the detector will determine how much spatial spectrally you can resolve things. And that essentially decides how much is the spectral resolution. And this is usually given by a number called resolving power. So at a particular lambda, I can get a spectral resolution of delta lambda. And this number you will see a lot in astronomy. Now, this number is also used, like for example, if you look at high redshift objects, right? I'm looking into a telescope to very faint objects. First of all, there is not enough light. These are very dim objects. Very small light comes. So if I disperse it very much, like each bucket of pixel will get to be fraction. So usually for very far away faint objects, we use low resolution. So around like 500,000 ish only we use. And you also derive that much science is only derived out of it. Now to get stellar abundances, suppose you want to know the chemical composition of a particular star, what are the components in it, what are the compounds in it, then you need higher spectral resolution, because then you need to identify these absorption lines. You need to identify absorption lines and what is the like the chemistry, which components are there at what ratio. So spectra can tell a lot about that, but that usually requires very large resolution. The other thing you require very large resolution resolving power is radial velocity. So let me see if it works. I think I need to play it. Okay, so this is a star, and this is a planet orbiting the star. Now, the planet's light I can't see. I'm only seeing the light of the star. Now, when the planet rotates, no, like there is like two bodies when they rotate in free space, the even the high mass thing will also little wobble, and these wobbles are like in the range of like meters per second, etc., depending on the size of the planets. Now this wobbles also, you can kind of, okay, this wobbles. So depending on where you are, again through Doppler shifts, you can see this thing shifting. So from this shift of the spectra, I can deduce what is the mass of the planet. So this is information I get. So this is another way to look at it. I am looking through, suppose I am looking straight like this. The planet is going like this. It has maximum velocity component in my direction and it will give a spectral shift. And that can tell you a lot about the mass of the planet. So the other thing is we can use it to identify things in exoplanets. So other stars also have planets that will be orbiting the star. Now some planets will like pass in front of it and they will have atmosphere. And their atmosphere is usually thin, some atmospheres are thin, so that light can pass through that atmosphere. But what happens is that when a planet has a characteristic composition, when the starlight comes through it, it adds little absorption features onto it. So what people do is through transmission spectroscopy, where the planet goes, they will look at the star alone. Then they will observe again when the planet is crossing them. Then you see like what extra things are coming. So if you see extra things in the spectra, then you think, okay, some component has come from the planet. And then that gives you an indication, are there certain things in that planet? Are there biosignatures? This is one of the technique usually used to check if a planet has biosignatures. But I think people will talk later about the science part of it, but it's a general technique. So, how much time do we have? 5 minutes? Okay. So I'll just conclude fast because some other techniques. We were talking about single object, right? I take one object ka spectra and I get the thing. Now there are things like multi-object spectroscopy. Sometimes I have this science thing that I'm looking at like a giant patch of sky, wide field. And my science case requires that I need spectra of everything in that field. Now with my tiny little slit spectrograph, if I go, I can't get the spectra of everything because it's isolates an object. So I need something to get a spectra of most of the thing. I can't simply also use slitless spectroscopy because everything will merge the spectra. So what people usually do, this is the single slit, it's only one slit. What people do is like want to identify, like have slits in different parts of the field. So there are many ways to go about it. What people do is that if you already know which area you want to look at, you can already make a mask. Like the Pringle box ka mask I made, I can make multiple slit in different objects and get a spectra. Other way is to have fibers that will like move around and catch different objects. That's another technique. It's just thoda complicated because you need the mechanism to move the fiber to a star. That's one way. Other way is to use configurable slit. So depending on where the object is, these aluminum bars will come close on to different objects and form a slit. That's like this. It will come from the side, form a slit, and give you a dispersion. So I just want to also, because I come from IIA and also some of the projects so this is one of this multi-object spectrograph that we were trying to build for this 3.6-meter telescope. So this is in Devastal, in Nainital. So currently in India, this is the largest optical telescope. The Hanley telescope we have in IIA is 2 meter. This is 3.6 meter. So it can see little bit far away also and like collect more light. So for this, we are building MOIS, which is a multi-object spectrograph. And Ravi talked about this 30-meter telescope, right? One of the big things in IIA is also because IIA and like a lot of institutes in India are part of the 30-meter telescope projects. So India is officially a partner. So we are also contributing to different spectrographs for the 30-meter telescope project. This is one such spectrograph called the wide field optical spectrograph. So it works in visible, it has certain wavelengths, and it's very sort of wide field. It's 8 arc minutes. So it doesn't cover the whole moon, like 1/3 of the moon size fields it can cover. And look at the size of this telescope. I told you with large telescopes, the instruments also become large because everything is large, the focal plane, everything. So look at the person here. So the telescope is somewhere here, and these instruments are housed in this platform. And this is one such instrument. So this person is here. There's like at least 3 floors, right? Size 2 to 3 floor size of this one instrument only. It looks like a giant dome. So that's the size of these big telescopes. It's very hard to imagine the scale of some of these projects. So I'll just conclude with there is one more interesting thing which is called integral field spectroscopy. We were talking about selecting objects and getting spectra of it. But another way people do is to use, you have a field, you sample the field in different spatial, you use something called a lenslet or like something to slice different parts of it and take a spectra. That gives you your entire field, you'll get a spectra of each single point. So that is also one of the ways people do spectroscopy. It is literally like a 3D cube. You will have your X, your Y, and you will have your wavelength. So this is like that. So this is a cube like that, and this is like a, so if you look, this is like a nitrogen line, and it's a galaxy. So when you go through this scan, right, you go through the nitrogen line, you see like all the star forming regions in the galaxy where all the stars form. There is a lot of activity. It lights up. So you can deduce a lot from this IFU data, which are 3D nature. So this is another one way people do it using this micro lens arrays and get these cubes. I came to it because we are also building in IIA this instrument. Ravi is actually heading this project in IIA. Together, so UC, University of California, Santa Cruz is the leading institute, but we are also part of it. And it's a direct imaging IFU, and it's one of the instrument built to detect exoplanets. So there will be some exoplanet on the side of a star. You block the star and get a spectra. This will be in Keck Observatory, and this uses something called coronagraphy, which is basically the star is too bright. The planets doesn't have much light. So the planets usually are like 10 raised to minus 6 in like the flux, the light. So if you have the starlight, it's very difficult to see the planets next to it. So what people do is like block the starlight, and it uses something called a coronagraphy to block the starlight. So if you see here, the starlight is blocked, and you can see the planets. This is one of the amazing exoplanet system, HR 8799. It's like a whole exoplanet system discovered by such technique. So we are doing this in mid IR. So this is the same system simulated how it will look like in our scales instrument, and it scales operates in this mid IR where this Jupiter's, right. So if you see Jupiter is here, Jupiter's flux, and when you go from here to here, the wavelength, the more you go to thermal infrared, the contrast between the star and the planet decreases. So it's easier to detect them. So I think I'll conclude with it. This is also one of our flagship projects at IIA. So I hope I gave you some flavor of what instruments are and spectroscopy. So I think I'll conclude it here. Thank you so much. So if you people who are looking at the light through the Jugadu spectrograph, if you haven't seen, you can come to me after the talk. I'll show you how to look through it. Okay. No, everybody's tired. Yeah. Yeah, yeah. Yes. 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 Yeah. Yes. 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 Excellent question. So this usually now there are two problems. One is I want to collect as much light. So usually fiber sizes are like 300 micron or 500 micron also you can get. But I have to make sure that most of light goes in. So I will ideally prefer larger size. But the larger fiber when it goes here, you get like larger size so that like the resolution decreases exactly as you said. So what people sometimes do is have a bundle of smaller fibers, like you will collect all the light in like a group of fibers, but when you come here you put all the fibers in like a straight line. So when it disperses, the single fiber that decides the resolution in this side is very small, and it's a very difficult, it's things that people are researching on how to reduce fiber size, improve resolution, etc. Good question. Yeah, yes. Yeah. Yeah. SETI, search for extraterrestrial. So currently there is so it's a complex question, as in like it's related to how we are doing for all the search in exoplanets, right? Like we are looking for the main driving factor of lot of funding, lot of research in astronomy for exoplanets is because we are interested to find out are there planetary systems like us outside, right? And a lot of media, the news is around. Do we find biosignatures? Do if we like you would have heard somebody says, okay, I found phosphine. So when you find phosphine in Venus, people it becomes a big thing. It was not true eventually, but phosphine is something that is produced by very biological things. So when it's detected, it becomes a huge thing. And in general, larger exoplanet community is also driven by like that. Now comes to SETIs for intelligent life. So we are not even reached the stage where we are detecting properly. We have not mastered the techniques to identify the building blocks of life in different planets. And it's a so parallelly SETI is there in US. SETI is a big organization also. They have a look for signals that are so it works in a way where you're looking for signals that are sent by other civilizations, and you are looking for it. Like it may be there, it may not be there, and they have been searching. Until now, we haven't found any, right? So, in the larger scheme of things, you need to search for like a large space in like different wavelengths, different field of view, etc. So, there is some trust to it, but I would say, like personally, what we are still perfecting like the smaller like even detecting smaller things from like bright things that we don't have the concrete technology to identify at this point. But Ravi is a more expert on this, so you want to contribute something there?